Welcome to our webinar for the month of June. We're going to be focusing on networking fundamentals, and we'll cover what those fundamentals are. And of course, our focus is on why they're important to wireless professionals. And at the end, I'll also introduce you to a new resource that we'll be making available in a couple of weeks on this very topic. Over the years, here at CWNP, we have had many requests from people to fill a gap that's out there in the market, and that is providing a solid general networking foundation that people can build on in their not only wireless career, but really any kind of networking career that they want to go into. And so we are launching what is called the Certified Network Administrator and Engineer certification, in the same line that we did the CNAE in December, Certified Python Network Administrator and Engineer, and this one will be focusing on networking in general. And I'll explain more about what that is when we get to the end. But for now, if you want to follow on social media, on X, I always want to say Twitter still, CWNP and Carpenter Tom, you'll find us there. And of course, you can always email me, tom@cwnp.com, if you have any questions. As usual, our session will be recorded today, and it will be archived on YouTube on CWNP TV within a week. Usually it's up by Monday, but I say within a week to be safe. Okay, so let's go ahead and jump right into the content. First of all, we're going to start with what are fundamentals? Well, it depends on the domain that you're working in, right? The fundamentals are the essential or foundational elements, principles, or concepts that underpin a particular subject, system, skill, or field. So they are essential. They are foundational. They're what you build on, in other words. They may be concepts or principles. They may be elements, objects, technologies. You can get very specific as to what they actually are, but they are the foundation on which everything in that knowledge domain is built. So if you don't have these, you can't go on. In the field of education, I often mention the concept that they refer to as threshold concepts. So threshold concepts are concepts that you have to know before you can move on to more advanced knowledge. And the reality is that when it comes to networking, there are foundational concepts that you need to understand before you can really move on to understand more complex ideas. The key thing to remember, though, is that fundamentals does not equal simple necessarily. In fact, some of the fundamentals of networking are actually some of the most complicated parts of networking. As an example, modulation is a fundamental, and yet it is more complicated than some of the things that you really don't study until much later on in your learning and understanding of networking in general. Interestingly, in the wireless space, we put a fairly heavy emphasis on modulation, whether we're dealing with Wi-Fi or other wireless protocols, because it has a big impact on the performance that you get on those networks. So, for example, if you are a farther distance away from the Wi-Fi access point, you will be using a lower modulation rate. That's why you have, in part, a lower data rate. And so understanding that simpler modulation can be demodulated with poorer signals explains to you why it is that as you get a weaker and weaker signal, you get a lower and lower data rate. It's because you're using lower and lower modulation rates, which are simpler than the more complex modulations that require a better signal or a higher signal strength or signal quality. So again, that's a fundamental. It's there in all of the networking communications, and yet it's not necessarily simple. The big thing to think of here, the way I like to say it, is a fundamental is something that you can't get there without going through this. In other words, you'll never truly understand the later topics if you don't really understand these. So fundamentals can be broken down into knowledge subsections, you might say, like design, troubleshooting, administration, operations, and so forth. When we talk about network design, we're talking about models, topologies, conceptual frameworks or architectures. Security is there. You'll notice security, I've put it in all three of these. Why? Because security is a cross-cutting concept. You really can't talk about any area of networking, or you shouldn't talk about any area of networking and not also be talking about security, because security covers all the layers of the OSI model, all the layers of the TCP/IP model. It covers all the components from a hardware perspective, all of the components from a software perspective, at every layer and at every area of the network. And so therefore, no matter what you're doing, security should always be in mind. Troubleshooting, of course, you have to understand hardware and modulation and protocols and security. And with administration, again, hardware, protocols, monitoring, evolving. So how do you grow an existing network as opposed to implementing a new one? Controlling, how do you make sure that everything is managed according to policies and procedures and so on. So all of these are part of networking fundamentals. And the interesting thing is that when you go on to study more advanced things, let's take, for example, with a specific vendor like Cisco, and they have their CCNA, which you might think of as their fundamentals certification, right? And then they have design certifications, and they have advanced certifications that focus on specific things like maybe wireless or security or WAN technologies. The assumption, though, is that you already understand those fundamentals. And in fact, there are many of the things in the more advanced certifications that you can't really begin to comprehend and understand without those fundamentals. We see the same thing in our Wi-Fi track, for example. You won't fully understand everything that you're learning in, say, CWAP if you don't already have CWNA level knowledge. And in the IoT track, you won't understand everything that you're covering in, say, CWIDP if you don't already understand CWISA. And so that's the key, okay? So we've got to make sure we have the fundamentals so that we can move on. One of the fundamentals that we talk about a lot is the OSI reference model, right? So we say, oh, you need to know the OSI reference model. Well, actually, you need to know it as a concept only because we use it as our dictionary, if you will, for discussions of networking. So we're often referring to technologies as to the layer at which they're operating, or for a given technology, as we're explaining its component parts, we may talk about this component works at this layer and this component works at this layer. And interestingly, even though we actually use TCP/IP or IP networking far more than any other protocol, we don't tend to use the language of TCP/IP as our language for referring to these communications. And so you have to understand the OSI reference model. Now, by the way, let me state clearly, my plan is not to teach you all of networking fundamentals here today, because that would take too much time. We would need a good 15 to 30 minutes, depending on how deep we wanted to go, just to get a good overview of the OSI reference model. I would suggest, though, that the OSI reference model can become more to you than just language. It can become a conceptual model that you use as a thinking tool. So when you're thinking about a networking problem, you're trying to position the problem, where it's occurring, what the symptoms are telling you within these layers. And then you're able to narrow down where you may need to focus your troubleshooting efforts. So that's the benefit of having something like this. It's not just that it's our language, but it's also our thinking, how we think about things. And there's a lot of discussion about, do we do away with the OSI reference model and just start talking about the TCP/IP model? I don't think we're going to see that disappearance happen anytime in the near future. And it does come down to the fact that it has become, among all of those in the industry already, their model for thinking about networking. And so even when they talk about TCP/IP, they talk about HTTP being an application layer protocol, but most people don't mean the TCP/IP application layer from that model. What they mean in their mind, in their conceptualization, is layer 7 of the OSI model. That's what they're actually thinking about when they say that. And so it's important that anyone coming into the industry begin to understand how people think. How do they conceptualize things? so that you can understand the communications. And these include written communications, right? When you're reading a white paper from a vendor, or if you're reading documentation from the vendor and you're seeing this kind of terminology, you need to know and understand what they mean. Also, as a thinking tool for how communications occur on the network, it becomes important. And we see that illustrated in this graphic, in that we do not have to go all the way up to the application layer at every node along the path from the source to the destination, right? So our middle nodes may only decapsulate up to a certain level, whatever they need to move the data forward in the communications track. And so we can understand how a router works versus how a switch works at a generic level based on thinking about the OSI model and what levels those devices are actually concerned about. Another fundamental concept to think about is the communication model. Now, I've intentionally chosen to go back in time, dig out an old book. This happens to be from 1985, a book by William Stallings. Took me a moment to get that name back out of my brain. William Stallings, and he's written many books on networking and security over the years. In fact, many people, when they go through college courses on networking or security, they're very likely to be using one of his textbooks that have been updated over the years. So this is all the way back in 1985 in a book called Data and Computer Communications. And it suggests that there's a source system and a destination system. There's a transmission medium between them. This is focusing on a single link. In that single link, from some agent, which might be a person, it might be a software application, but from some agent, you're feeding input to the network communication system. And then there's a transmitter that transmits it. It takes this data and converts it into whatever signal format is required for this network. It then goes across that medium, whether that's wired or wireless or what have you. The receiver receives that signal and then attempts to demodulate and decode it, which results in an output data or signal that is then sent to the receiving side agent, which may be a person or an application. Now, the reality is that what was received may or may not be what was sent. That's the reality of any communications channel. It's true even when it comes to verbal communications when we're talking to somebody, right? So if you're talking with someone, having a conversation, they may not receive everything that you send. They may miss some things because they're distracted, because there's noise in the environment that makes it so they can't hear you as clearly as they would like to, and so forth. But that doesn't mean they don't get the overall message, right? So they might miss a syllable, but still be able to logically deduce what the word was that you said, even though they didn't actually receive it in a way that was clear. Well, we do similar things in our communication channels because we understand this concept that what the receiver receives may not be what the transmitter sent identically. We have methods for dealing with that and trying to allow the overall message to still get through, even though individual tiny little components of that message may not have been received as they were originally transmitted. And so what this does then is we think about a model like this is it causes us to think about those issues that we need to address. There needs to be some kind of an interface, right, between the agent and the transmitter. There needs to be some kind of a signal that we send on the medium. And that signal is going to be different if it's Ethernet cable, or if it's a wired Ethernet versus fiber, or if it's wireless. If it's wireless over long distance versus wireless over short distance, right? All of these things end up telling us what our medium is and then will impact the signal that we choose to use on that medium. And then, of course, we will have to think about how we're going to deal with making sure that the receiver knows that the transmitter is sending a signal and that it's not just seeing some kind of random energy, but that it is somehow a represented signal. So that's a concept we need to address, and that's what we call synchronization, right? So these are all things that they begin to come to mind when you think about what you need to make communications work just on a single link. We're not up yet at the level of thinking about how do we get 10,000 devices in a large enterprise network to all be able to communicate with each other, or at least be able to communicate with the data center and the data center back to all of them. We're not even at that level yet. We're just talking about a single link so that one device can ultimately talk to one other device. And so when we think about that, what we're talking about is system level communication, right? So these are the tasks that we have to think about. And all of these tasks are focused on using this transmission system that we have as efficiently as possible. And these things here are what I call, when it comes to networking in general, the forgotten fundamentals. Because networking in general, people often want to skip over all of this and just jump right up to, say, things like IP address management and all of the higher level things that make our large scale networks work. But when it comes to troubleshooting a problem on the network, quite often understanding these concepts, many of which impact that local link, become very important to being able to troubleshoot that. And so the interface itself, right? So we're talking about a network interface card or a network adapter, as it's sometimes called, whether that be a wireless interface or a wired interface. Signal generation. How do we generate a signal? What about synchronization? How does an Ethernet device synchronize with a remote Ethernet device? Does it have some way to let that remote device know, hey, here's an incoming signal. You need to be prepared to receive it? Does a 802.11 Wi-Fi device have some method of doing that? So these are the concepts of synchronization, and this is done usually through, in networking protocols, some kind of a start of frame delimiter, a preamble, whatever you want to call it, but some series of signal bits that are really just fixed waveforms, fixed signals that say to that receiver, this is not just noise. There's an incoming communication. And so you need to use this stuff that's not just noise to synchronize as a receiver so that you can do signal reception. And that's not something unique to wireless. You know, there are many people that work in networking on the wired networking side for years. And then they come over to Wi-Fi and we start teaching them all about physical layer headers and training fields and these concepts, and they start hearing about them and they think, wow, this is a lot more complicated in wireless. Well, it is more complicated in wireless, but it's not that these things don't exist in wired networking. They're there too. It's just that it has become standardized over the years, and generally speaking, you plug in an Ethernet client to an Ethernet switch port across some type of a, say, Cat 6 cable or Cat 5 or whatever it is cable, and they just negotiate and work. And so people don't necessarily think about it or pay attention to it. But what happens when they don't work? Or what happens when they're not working the way you expect them to? Like you're getting a 10 or a 100 megabits per second connection on what you thought was a gigabit link. What happened? Why is this taking place? It may be a cable problem. It may be a cable length problem. It could be, any number of things, right, that could impact that. And the thing is, because we don't bother to learn that level of information for networking in general, like we do in the wireless space, sometimes we fail to be able to properly troubleshoot what's occurring. So these are important things. Then there's exchange management. This is about how the communication process takes place. Any kind of back and forth communication. Are there acknowledgments in the process, or are there not acknowledgments in the process? This kind of thing. Then there's error detection and correction. So this has to do with that fact that I said what the receiver receives may not be what the sender sent, right? It could detect it as something different. Now, to be clear, what the receiver receives is what the sender sent, but it may have been changed by some things, and most often interference and attenuation and so forth. So the point is that there comes a point where that receiver begins to lose the ability to receive and demodulate and then decode everything perfectly. So what we can do is we can mathematically manipulate what we're sending so that the receiver can correct for those kinds of errors. That's error correction. And this is an important concept on the wire as well as in wireless communications. Flow control, not exactly the same thing as exchange management, because flow control is about making sure that we don't saturate the target. So that target has some largest frame size that it can receive. It has a buffer size to be able to handle things while it's processing them and things like that. And so flow control is about making sure that as we're transmitting to the receiver, we're doing it in such a way that the receiver can work with or accommodate our communications. And some of this is managed at higher layers and some of it at lower layers, but it's an important part of it. Then there's addressing. How do we indicate the intended target for our communications? There's addressing that happens down at the lower layers, at OSI model layer 2, right? And then there's addressing at layer 3. And there's even a sort of addressing, port addressing at layer 4. And so we have this concept of saying, here's my target. And that's what addressing does for us. So addressing can be within a host, here's the target, or it can be within a network, here's the host, or it can be starting from my local link, here's the network I'm trying to get to, right? And then it can also just be, hey, I'm here, you're there, here's the data. That's that layer 2 level, right? I'm just sending it to some other target that's on the same layer 2 network as me. And that could be because the ultimate goal is to get it to some far remote destination. And to do that, I've got to get it to my local target first, right? Just like if you send mail through the post office, you got to get it in the mailbox first, even though the mailbox locally is not your ultimate destination, is it? You're trying to get it possibly all the way on the other side of the world, but you got to start by getting it to that first node on the postal network, and that is your mailbox. Then we have routing, of course, which can be based on, obviously, our addressing. And today is mostly IP routing that we deal with for the vast majority of communications. Recovery is a little different concept in historic network communications and network fundamentals than error detection and correction. So error detection and correction is something we mostly focus on layer 2, possibly layer 4 as well with TCP. So we've got some layer 4 and down stuff, but recovery was really more of an application layer concept in earlier networking documentation and materials. And so the concept is that you've got an application on one device and there's an application on the other device. And the client may simply be making a request of the application on the other device to change something in a database or change something somewhere in the application's logic. And the thing is that client device needs to be able to say there's a state that remote system is in, and if it follows my command, that state will change. But if it fails to follow my command, that state will not change. So I need to know the state of that remote application and therefore know what my next step is. And this is where this concept of recovery really comes into play in historic thinking with network communications, that we need to be able to communicate back to that client, hey, we're not in the state you think we're in because you submitted this request for a data change. We were unable to change the database, so you need to start again in the old state you thought we were in. So that's really what this concept of recovery is about in this context. So not the same thing as error detection and correction. Then there's message formatting. Again, it's really an application layer concept for the most part. We're structuring how we're talking from one application to another application on the network. And then finally, there's protection and security, which, as I said, is a cross-cutting concept that always has to be thought of everywhere across the systems. Now, with all of that, let's answer a simple question. Why do we have cable length limits on wired networks? I mean, why can't we? It's in the wire, right? We don't have all the interference problems that we have on a wireless network. So, why is it that we'll just say 100 meters. Why is it that I have a 100-meter limit? Why can't I just run 500 meters on a Cat6 cable or a kilometer on a Cat6 cable? Why do I have limits on that cable? You see, knowing the answer to this is a part of the fundamental knowledge that's important for networking administration and operations and troubleshooting and design, because what it comes down to is everything attenuates no matter what medium it is traversing. Now, it will attenuate differently as it's utilizing a different kind of medium. So in other words, signals will attenuate differently on a cable or on fiber with optical communications or on wireless. It'll attenuate differently. In other words, attenuate a different amount at a different distance, right? But there's still attenuation. And the point is, if I'm saying I've got let's go old school here. I've got a 10 megabit Ethernet adapter connected to a 10 megabit switch port. So they're negotiating good old 10 base T. Then the reality is there's a limit that fixed modulation that is 10 base T will work at before the signal is so attenuated that the receiver can no longer demodulate the signal appropriately. All those concepts you may have learned studying wireless with us, they apply on the wire as well. It's just they apply differently because we're dealing with a wire instead of dealing with wireless signals. But attenuation is still there. And this also impacts things like PoE, right? So if you're implementing power over Ethernet, well, just like your signal attenuates over distance, in other words, the signal becomes weaker. Well, what is that that's becoming weaker? It's energy, right? So if I'm trying to provide energy to a PoE device across a cable, guess what? That power also attenuates over distance. And so there's a point at which I'll no longer be able to achieve the expected power for that PD, that powered device, at some distance. And therefore, I have limits to my length for that reason as well. So it's important to know that these things are there for a reason, and they're born out of the fundamentals. So the concept of the fact that I can't have a PoE cable, or for that matter, a data cable, longer than a certain length and still achieve a particular data rate or a particular power level, that is born out of a fundamental that signals attenuate, that energy attenuates as it travels down a wire. And so therefore, I have those higher level rules that I think about for PoE, for data communications, and so on. Now, IP networking is different, right? So we talked about the OSI model. At the application layer, we have our applications that run. At the transport layer, we're all about transporting the messages from those applications. At the internetwork layer, we're about getting those messages that need to be transported from a local network to a remote network, if needed, or maybe we're staying within the local network for some communications, but determining where we need to go to get where we're going. And then the network layer is down at the city street level. So a good way to think of it is like your application, well, that creates these messages that need to ride a bus. The transport layer gives you the bus. The internetwork says, hey, ultimately, if you really want to get to that destination you're talking about, here's the large scale, the Rand McNally map. In the old days, in the United States here at least, we had these Rand McNally maps, which were pretty big. You'd hold them up and you certainly wouldn't want to drive while you're using it because it covers your entire windshield. Truckers used them and, I had to for some various reasons I won't get into when I was younger as well. But this was before the age of, maps on your phone and GPS that kind of brought it all together. But then when you get to that local network, the Rand McNally map really didn't help you very much. It might get you to the city, but once you get to that city, you needed a street level map. And you might be able to stop by and get a street level map at a local gas station or something back in the day. I doubt you can even get them anymore. But it used to be really common that you could go in and you could buy a street level map for the local city. And then you would unfold that to an even bigger thing, multiple feet by multiple feet, and you could look at your city streets. Well, those city streets are kind of like the network layer here. That's about how do I get around locally. And then the Rand-McNally map, that was kind of like your inner network layer. And then, of course, the bus is what we're traveling in, using those maps to get from my original application to the destination application at the remote end. How does it relate to the OSI model? It doesn't exactly, but we generally do something like this. So we have this conception that we have in our mind of these 7 OSI model layers: physical, data link, network, transport, session, presentation, and application. But what we're actually using in the real world is the IP model: network, internetwork, transport, and application. And the network layer of TCP/IP roughly equates to the data link and physical layer, and the internetwork layer to the network layer, and transport to transport, and then application to the top 3. And this is why over the years, some people have referred to layers 5 and above as the don't care layers, because if you're the network administrator, your job is to make sure everything from the transport layer down is working. And then it's a server administrator or a desktop technician or something like that that's responsible for fixing any local device problems. Because all that stuff up there at layers 5, 6, and 7, and some of layer 4, but certainly 5, 6, and 7, is really all about the local device and what's going on that device. And in the earliest days, it was always and only about what's going on the local device. Now we do have on our network things called application layer firewalls that might be implemented where we're actually filtering at application layer communications. But historically, you go back 20 years ago and beyond, we really didn't care much about layers 5 through 7 at all. We were focused mostly on layers 1 through 3 and maybe some filtering based on TCP ports here and there. But 95+% of our work as a network administrator was down there at the lower 3 layers of the OSI model, the lower 2 layers of the TCP/IP model. And then when it comes to the hardware, well, your 3 primary building blocks to have the network to which you can connect are switches, routers, and cables. When it comes to wired network connections, that's it. That's the core. Switches, routers, and cables. And if we think about it from the layer perspective, we tend to say that a switch is layer 2, and a router is layer 3, and the cable is layer 1. So that's how you might see it referred to a lot. Now, in reality, a router, as I said, may have functionality all the way up to layer 7. And a switch may as well. There are application layer switches. And so just because from a hardware perspective, it's a switch, doesn't mean that it cannot do anything at higher layers. It's just historically the general purpose of a switch is to build that Ethernet or layer 2 network. And the historic purpose of a router is to build that IP or layer 3 network. And then the cable, it just gives the layer 1 medium across which the communications can happen. But it's important to note that the actual modulation onto those cables happens within the switch, within the router, within the end devices. I often say when we're talking about wireless communications, I say that antennas are stupid. And what I mean by that is that even if it's a smart antenna, it's still stupid. The intelligence of a smart antenna is behind the antenna, because the antenna, the actual thing that radiates or captures signals, radio frequency signals, that actual thing is just a physical component that exists in reality, and things happen to it. It doesn't make anything happen. And this is true for both transmission and reception. The antenna doesn't make the energy radiate into the air. It simply exists in physical space, and when the device connected to it imposes the right energy onto it, it leaks. It doesn't decide to leak, it just leaks. And that leaking is what we call radiation. It's really that simple. So the antenna doesn't make a decision to leak. It can't help but leak. Okay, it just happens. It's like a bad tire, right? Well, the same way, these cables, think about it. You've got cables all over the place, either at your home or at work. Do they ever do anything? No, they don't do anything. Cables are stupid, just like antennas are stupid. They don't do anything. They simply exist in physical space, and then a device, such as a laptop, a desktop, or an appliance or a server, a device to which that cable is connected, imposes a signal onto the cable. And then the receiver simply sees that signal coming out the other end of the cable. The cable can't even decide, I'm not going to let that signal come out. It has no choice in the matter. It simply exists as a physical entity in the universe that abides by the laws of physics. We take advantage of those laws of physics by imposing the right thing on one end to get what we desire out of the other end. In the same way that we impose the right thing on one end of a wireless link so that a receiver on the receiving end will, just by nature of its existence, capture that incoming information. And again, even if it's a directional antenna in wireless, it's still stupid. We have simply engineered that antenna to be directional in the way that it behaves. But the antenna is not deciding to do that. And even in smart antennas, as I said, the intelligence is behind them, deciding on how to use the antenna, or if there is a motorized element, how to aim the antenna, or anything like that. It's all happening behind it. The actual antenna itself is stupid, and the actual cable is stupid. All right, well then what do we mean then when we say we've got a faulty cable? Well, we mean that there's something wrong in the shielding. There's something wrong in the internal wires, something like that in the cable. There's something wrong with the connector on one end or the other, making it so that it doesn't make a proper connection. That's a faulty cable. If you plug in the wrong cable, you might get a 100 megabit link instead of a gigabit link. And that has nothing to do with the cable making a decision. I made the decision, and it was a wrong one. And because of that, I don't have the highest data rate that I could get, right? So when I talk about understanding the fundamentals, all the things that I'm talking about right now, these are the things that allow you to ultimately become an expert troubleshooter, an expert designer, and so forth when it comes to networking, whether it's wired or wireless. Understanding the fundamentals and really understanding them allows you to do that. Some concepts you must know to understand networking in general: segmentation, right? How do I break a network into different segments for optimal purposes? So there are two concepts here, right? There's the technical way we segment our networks, and then there's the reason why we do it. So at the fundamentals level, you're mostly learning the technical way we do it, using a router, for example. And then at the more professional level of knowledge, you're understanding why you make the decisions you make for segmentation, the performance advantages it gives you, the security enhancements that it provides, and so forth. Then there's IP address management that we're thinking again at a higher level. So at the lower level, we just need to understand what an IP address is. We need to understand what a default gateway is and how a router allows one IP network to talk to another IP network, etc. All those technical details, right? But IP address management abstracts that up to a higher level and says, now you can go to another level and you can begin to think about how to properly manage IP addresses. In other words, what size should my IP subnets be? How should I organize the addressing that I'm using on my IP subnets so that it's easier to manage and administer over the long haul, etc.? These are things that are born out of the fundamentals. There's a technical side to it, then there's the conceptual, logical side to it as well. Then network services, right? You've got to understand the basics of DHCP, DNS, NTP for all modern networks today. The network tools like your protocol analyzers and troubleshooting tools and monitoring tools all need to be understood. Then you've got to know things like network perimeters and zones and firewalls, and I'm not even done with the list. This is just to give you an idea of all of these various things that we need to understand. Now, I suggest that even if you're not going to specialize in security, right? You need to understand at least the fundamentals, but I would suggest if you're in the industry for more than 5 or 6 years, by that time you should go beyond the fundamentals of security and probably have a good professional level knowledge of security. I do understand there are people that specialize in it, and in larger organizations, they even have people dedicated to it. But the reality is that security is cross-cutting, and everyone that touches anything about the network is going to have some impact on security. So this is why, by the way, we have policies that often come to us from people that are professionals in the security space, and then we may not understand why we're doing them, and so we skirt them. We don't always do things according to the standards. Well, it's an important thing to think about and understand that doing that may be causing a security breach in the organization because you don't understand that more advanced level. So do you have to become a master of security to do anything in networking? Certainly not. But I would suggest that as the years go by, you should be becoming more and more of an expert in the security area of networking, because it is something that's going to impact every area that you touch with networking. Now, one last thing I want to mention, this also falls into my category of forgotten fundamentals, things that a lot of people, they don't even hear about it anymore in the educational process of networking. And they are some of the theoretical concepts that really gave birth to the networks that we use today. Information theory, network theory and graph theory, queuing theory, flow control theory. I'm not going to get into them in detail here, but these are some underlying theoretical concepts. I mean, some of them date all the way back to the 1930s, but they end up being applied in very practical ways within network environments. There's a mathematical reason why a network that is segmented in a particular way performs better than that same network of end devices segmented in a different way. And it comes back to network and graph theory. There's a reason why you need a certain quality or level of a switch or router at one area of the network and a different in another, which comes back to queuing theory and flow theory. So the point is, these underlying theories, which we address in brief in the new CNAE, we can't go into extreme detail on them because you could literally study any one of these for multiple semesters in college, for example, right? But it's important to grasp that there's a reason behind what we do beyond just do this to get that. Because when you understand the theory at a basic level even, then you're better prepared to understand what you need to do in a given situation when there's no one there to tell you do this to get that. And now it's completely up to you to figure out what the this is that you should be doing in order to get that which you're after. So theoretical concepts do play a role as well, and I think they're very well worth visiting.